Complex roots come from when we are trying to solve the quadratic formula, but we result in the discriminant having a negative value. Let's look at what I'm referring to. So the quadratic formula that we have been working with, this is used to solve for the variable in a quadratic equation. For example, if the equation is written in the form ax squared plus bx plus c, which is standard form for a quadratic, all values are on one side in descending order set equal to 0, then to solve for the variable x, the value for x that makes a true statement, the formula is the opposite of the b term plus or minus the square root of b squared minus 4 times a times c, and all of that is divided by 2a. It's very important that you write the value of the variable itself that you are solving for, and also that you set up the entire quadratic formula accurately. Now, the part of the quadratic formula underneath the radical, this part right here is called the discriminant. It has a very special name. So the discriminant, what the discriminant does is it tells us how many roots or zeros we should be looking for. For example, if I take just the value underneath this radical, it's not the radical itself. If you notice, it's just the operations happening underneath the radical. And I set that discriminant equal to 0, or if I look at the value of b squared minus 4 times a times c, and that whole value is equal to 0, what that means is that we have one real root, or it means we have 1 0. Another thing that we could say is that it means that we have one solution. All of those mean the same thing. I'm writing equal signs in between them because I could say any one of these and have it have the same meaning. And what that means is that as we start graphing equations, what that means is that you're going to get a parabola. It may open up or down, but what it does is it's going to touch at exactly one place on the x-axis, and that's going to be my real root. Now, if I look at the value of the discriminant, and I get a positive value, the way we write a positive value is we say it's greater than 0. So it doesn't matter what the positive value is. It could be 1, 2, 37. What this means is that we have 2 real roots. Right? Again, if I look at what that also means in terms of what I wrote earlier, that means that I have 2 zeros or 2 solutions. Another thing that this we can start thinking about is the number of factors that we're having when we set up our equations. So a lot of what we've talked about before is going to come back. So again, if I were to graph, again, it can open up, it can open down. That's not the issue. It's just about what the meaning of a discriminant where it's set equal to 0, or sorry, a discriminant that's greater than 0, that it's going to cross my x-axis in 2 places. Now, the main focus of what we want to talk about today is what happens when the discriminant is less than 0, meaning a negative number. And what happens is I have no real roots. But what I do have is I have 2 imaginary roots. Imaginary or complex roots. Right? And so what this means is that I'm going to have 2 answers still, but the 2 answers are going to tell me something different. All right? So I'm going to have what we call 2 imaginary or 2 complex solutions. And with complex solutions, even though they're answers, this does not tell us where the graph is going to cross the x-axis. So what's going to happen is I'm still going to have a parabola opening up or down, but it's going to hover somewhere on the other side of an axis. It's never going to touch. So even though we have solutions to the quadratic, the solutions actually tell us when they have a negative discriminant that the graph is hovering above or below and does not actually touch this x-axis here. So it's really important that you understand the difference between a real root, something that really does cross the x-axis, and a complex root, something that tells me that I'm hovering. So because we get a negative number under the radical, something that we need to look at is how are we going to simplify a discriminant that is negative. So imaginary numbers or complex numbers, actually let me get this down. So a complex number looks like this. We say a plus bi. And the I is written in like an italicized notation, where the a itself, this is the real number portion. And the bi, this is the imaginary portion. And what happens is that when we were dealing with the quadratic formula, we're going to start noticing, for example, we're going to have an a plus or minus something that's going to happen. So right now, this is going to be what a complex number looks like. Just move my paper up here. And so let's look at what happens. How do I get, like, what does this I actually mean? So in Math 2, what we talked about is we talked about when you take the square root of a negative 1, right, that you have the 1, the square root of 1 is 1, but this negative in here tells me something different. I have to be able to say anytime I see a factor of a negative 1 underneath a radical sign, I'm going to use the little italicized I to let people know that there is a difference between having a positive value under a radical and a negative value under a radical. We also need to remember a rule for radicals. One of our rules for radicals says that if I have individual factors underneath a square root sign, that each individual factor can be placed underneath their own square root and then simplified as needed. For example, if I were to simplify the square root of 16. The square root of 16 is a perfect square. The number that I can multiply times itself to get 16 is 4. So 4 times 4 is 16, and so the square root of 16 is 4. It's the value that makes that square root a true statement. However, as we start changing those, you're going to see something different happening. For example, if I put a negative underneath that square root with the 16, now I don't just have factors of 4. What I have is I have a factor of negative 1 times a 4 times a 4. And what we have to look at is what happens when I break apart the factors of 16 and negative 1. The negative 1 gets its own square root. So does the square root of 16. So the individual factors that make up negative 16 get their own roots. Well, I have to know the difference between having a negative underneath the radical and no negative under the radical. So even though the square root of 16 is 4, I have to also take the square root of negative 1, which is defined to be the letter I, so that way I can tell somebody the difference between the two values. So they will look very similar in terms of the number portion. They both have the number 4, but the I tells us that there was a negative under the radical sign along with the 16. Again, for example, the square root of negative 25. Well, this can be written as the square root of negative 1 times the square root of 25. And since 25 is a perfect square, I can write the value of the square root of 25, but I have to include the fact that there was a negative under the radical sign and add the I, which again is the square root of negative 1. So as we begin working with the quadratic formula, we're going to go and start seeing other larger numbers underneath the radical sign that are not perfect squares. So your process for simplifying these roots does not change from having a negative or no negative. For example, when I look at the square root of 48, that is the same thing as negative 1 times 3 times 16. So I have three factors underneath the square root sign. I have my negative 1 root, my root 3, and my root 16. And every perfect square needs to be removed. So again, the square root of 16 is 4. The square root of negative 1 is I. And the square root of 3 is not a perfect square, and so that must be left underneath the radical. So this is the strategy that we want to be able to take when simplifying our roots, just as we did when we were working with the quadratic formula where we had positive roots. So this is the only difference, is the fact that we need to factor out that negative under the radical sign and change it to an I. So what we're going to do now is we are going to solve a few problems dealing with the quadratic formula where our answer is going to have this imaginary or complex root portion. Now it's very important that we follow all of the steps and the directions, as you'll be asked to do the same thing for full credit on your homework. And for example, let's say we have the equation y equals x squared plus 2x plus 4. Now, you have the option of trying the quadratic formula or trying to factor, but when we factor, we are looking for a product of two numbers that multiplies to get me a 4, but adds up to be 2. And that's just not possible. So previously we said this is not factorable. And right now it's still not factorable. But we can still solve the value that makes this equation true. There are still possibilities. So the first thing that we are going to do is we are going to set this equation equal to 0. Because in reality, when y is equal to 0, that gives us values that are going to hit the x-axis. Because all of your values on the x-axis are some sort of value where you have an x value, but the y value is 0. Doesn't matter if you're at negative 2, negative 1, 0. Every value that touches the x-axis has a y value of 0. So that's the first step, is to make sure we're set equal to 0. Now we're going to look at the values of a, b, and c. So quadratic formula is still the exact same. And again, remember that when you are trying to set up the quadratic formula, whatever variable is sitting here in your equation, that's how you're going to start. I'm solving for x, and it's equal to the process of the quadratic formula, which is the opposite of b plus or minus b squared minus 4 times a times c, and that entire value divided by 2 times a. Now, once you set up the quadratic formula correctly, we can simplify the discriminant. Remember, it's negative 2. Don't forget the plus or minus. And what happens underneath this radical is the 4 is by itself, but then negative 4 times 1 times 4 is a negative 16. And so I'm going to see that when I simplify underneath that radical, I'm going to get negative 12 under the radical sign. But I'm still keeping my process the way that I'm supposed to in terms of my setup. Now this is where I need to simplify this radical down. So the square root of negative 12 is the same as negative 1 times 4 times 3. And since I'm running out of space, I'm going to simplify down how I'm going to break negative root 12 down just like I did in previous examples like negative root 48, negative root 25. So the square root of 4, remember all of these are still under the radical. The square root of 4 is 2. The square root of negative 1 is I, and the square root of 3 is 3. Sorry, square root of 3 is root 3 because it's not a perfect square. And what you have to remember is that you're not done until you can simplify all of these values on the outside. And so when I do that, the values for x that are going to make this equation true, and again, x is equal to, we need to start our little set. 2 goes into itself once, 2 goes into negative 2 once, and 2 goes into positive 2 once. So I end up with a negative 1 plus or minus an I times the square root of 3. And that is going to be how I'm going to write my final answer. Now this really is two separate answers. It's still minus 1 plus the I root 3 and minus 1 minus the I root 3. But on a lot of our work that we've been working on, we're leaving the answer like this for now, and that's okay for the moment. So let's do a couple more because it's very important that we have this process down. But again, it's not much different than how we used the quadratic formula before. We just need to remember that when there's a negative under the radical sign, to create an I to pull out the negative. Also, let's look at how this is set up. It's nice, neat, and organized. Steps are contained here with the equal sign, so I know how one step flows from the other. We're simplified down as much as possible with our final answer shown. And again, we started the whole process with the variable and what it's equal to. So now I'm going to change what the variable is, but the process will still be the same. So I have an equation where y is equal to n squared minus 4n plus 6. Now again, my first step is to set this equal to 0 because I want to see, does this cross the x-axis at all? Again, that's when y is equal to 0. And since my variable is n, when I start my quadratic formula, I'm going to set n equal to, and I'm going to set up my quadratic formula. Now for me, it's a lot more helpful if I still go to the side and say that a is 1, b is negative 4, and c is positive 6 before I get started. And so again, let's set up our quadratic formula. Okay. So n equals the opposite of b. So if b is a negative 4, the opposite changes it to a positive 4. Plus or minus b squared. So negative 4 times negative 4 is a positive 16. Minus 4 times a times c. And all of that is being divided by 2 times a. And so 2 times 1 is 2, and that way I don't have to write down an additional multiplication. And so that's my setup. Now, leave the 4 on the outside by itself, but I need to simplify down what is happening under the radical sign. So negative 4 times 1 times 6 is a negative 24. That's still all divided by 2. So 4 plus or minus. Now again, I'm going to get a negative, and I just need to think about what value that's going to be. So it looks like it's going to be a negative 8 divided by 2. And so under my radical sign, I have a negative 1, a 4, and a 2 as factors underneath my radical. So again, the 4, the plus or minus, that doesn't change. The square root of 4 is 2. Square root of negative 1 is I. And the root 2 stays under the radical because that's not a perfect square. So again, I'm not done until I look at these values on the outside only. I put a little heart around them just to know that I'm looking at only the right pieces. So 2 goes into itself once, into this 2 once, and into 4 twice. So the values for n are going to be 2 plus or minus I root 2. And again, I was solving for n, so n is equal to those values. We're not going to use x, even though x is in the quadratic formula as a generic value. All right. We're going to use n. Now for our final example for today, what we're going to do is we're going to give a challenge problem. And we won't know exactly what the roots are of this problem. It's just going to look a little bit crazier. For example, 5b squared minus 5b plus 2 equals 3b squared minus 3b. And some of our work we've done before has had terms on different sides of the equal sign. And so we're going to have an example like that just to remind ourselves how to do the work. So I want to make sure that I move terms to the side that will keep the coefficient on the square term positive. And so it means that I'm going to subtract and move my terms from the right side to the left side and line them up underneath the correct term in columns as we've worked on before. So what's going to happen now is I'm going to end up with a 2b squared minus 2b plus 2 equals 0. Both of these are going to cancel out and create a 0 on the right-hand side. Now, because I am using the quadratic formula, it's not necessary for me to factor out this 2. I can, but it's not necessary. So if I want to use the quadratic formula the way it is, then that means the a value will be 2, b is a negative 2, and c is a positive 2. Now, it is beneficial to factor out the 2, but I want to be able to show you that it's not necessary, in case you're not sure. Now, the silly thing about this is that the variable b is what I'm solving for, which is not the same thing as this b right here from the quadratic formula. All right, so these are just the values, these are the coefficients, and this is to use in the quadratic formula. So don't get confused with the formula setup and the fact that there is a b in the formula itself. So I'm still solving for this variable b. Right. So it's going to be the opposite of the coefficient, right, plus or minus the square minus 4 times a times c all over 2 times a, which in this case is 4. So just be very careful that when you're using the quadratic formula, that sometimes worksheets you're going to have will have the variable b, and it's not the same as this one. Okay. So let's simplify down what we've got. I've got my 2 plus or minus root 4 minus 4 times 2 times 2. This is a minus 16 all over 4. So again, we're going to leave the 2 on the outside. 4 minus 16 is a negative 12. And again, when I simplify this down, I have a negative 1, a 4, and a 3 as the factors that create negative 12. So 2 plus or minus square root of 4 is 2. Square root of negative 1 is I. And the 3 is still left under the radical with a 4 at the bottom. Now when we simplify this, it's going to be a little different than it was previously, because 4 doesn't go into 2, but they still have factors. So I'm actually going to start from the top and say if I remove a factor of 2 from here, and a 2 from here, and a factor of 2 from here, that this is going to give me an answer where the value for b is equal to 1 plus or minus I root 3 over 2. And another way that we could write that is to write it as individual fractions. 1/2 plus or minus I root 3 over 2, where we separate out the plus or minus into the individual fractions based off of the denominator. So these are just a couple of examples of how you're going to be factoring using the quadratic formula, solving equations where you have real or complex roots.